Um, Good morning, good afternoon, and good evening to everyone who just joined us for another instance of the workshop on program synthesis, which is part of a Simons Institute program on theoretical foundations of computer systems. We will have 4 presenters today, 3 longer talks and 1 shorter poster-style presentation. We'll start with Todd Millstein from UCLA. Todd is a professor at UCLA, got his PhD at the University of Washington. His advisor was Craig Chambers. Todd worked on a huge range of problems in programming languages, from language design, optimizations, and other implementations to predicate abstractions and other aspects of program analysis, languages for various domains. And today he'll talk about inference of invariants, which you could think of as one branch of program synthesis. With that, Todd, thank you for joining us today. We look forward to the talk.
Oh, great. Thanks, Ross, for having me. Okay, so you can see the screen. Everything's good? Okay, great. So yeah, I'm going to talk about some recent work on inferring representation invariance. I'll tell you what that is, but I wanted to kind of back up a little bit first and give kind of some of the bigger picture. So, if you look today at where some of the most exciting, I think, interesting work on getting strong guarantees for real systems is, it's in the context of people using these interactive proof assistants, for example, Coq and Isabelle, where the human is kind of directing things and providing the program and in an interactive way and the specification, and kind of writes these proof scripts which use forms of automation that the proof assistant provides. And the proof assistant is giving a bunch of things. It's giving kind of bookkeeping, telling you where you are in your proof and what sub goals you have remaining. And it has these language of tactics where you can write little proof automation scripts, and it's giving you feedback on errors. And people have done real things with these tools. Probably the most notable one is the CompCert verified C compiler. And there's been others over the years, OS microkernel, verified web browser. And the bottom line is that this stuff actually works. A good example of this is that, there's been a lot of work on tools for finding bugs in compilers. C-Smith is one prominent example. And in their paper from 2011, they said, we found bugs in all these C compilers. CompCert's the only compiler we tested for which we can't find wrong code errors. And they say this is not for lack of trying. We devoted about 6 CPU years to the task. So actually going through this effort of having provable guarantees actually means something. But the problem, of course, is that it's crazy expensive. And so, this is from the paper on the verified OS microkernel, SEL4. So the spec they wrote took about 4 person months. That's not that bad. It took about 2 years to write the actual operating system implementation. Then they wrote it in Haskell, then they converted it to C. That took a little bit of time, but not very much. But the proof cost was 20 person years. So, so clearly there's an issue here, which is that, this stuff is really promising and exciting, I think, but really just too much time and effort involved to use this. And so you can ask, well, why is that? And there could be many reasons, but one observation that I'll make is that the kind of proof automation that these tools provide today is largely what I'll call local automation, meaning, within a single lemma or a single theorem. So they help you say, I want to prove this lemma, and the tool will kind of do small proof automation within there to help you prove that lemma. But what I'll argue is that what we're missing is automation for what I'll call the larger scale proof architecture. So if you think about it, when you give, just like with a program, if you give a specification, it's not just the end-to-end specification that matters. You have to then decompose it into lemmas for individual modules. Those lemmas might need other helper lemmas. Lemmas typically need to be strengthened so that they can be proven by induction. They're module-wide or system-wide inductive invariants. So the whole structure, the whole architecture of the proof is something that right now the human has to come up with on their own. They have to kind of come up with the whole structure and say, these are the lemmas I want to prove. And then within each of those lemmas, the proof assistant will help them. And so the observation is that these are all program synthesis tasks. Specifically, these are forms of invariant inference. So finding the right helper lemmas, finding the right strengthening for a lemma, finding the right inductive invariants, these are forms of synthesis. And so And so the argument is that synthesis really can be at the heart of what can make these kinds of interactive program development and verification systems more practical. And so this is what I've been doing in part for the last 5+ years, is forms of automated invariant inference. So that's kind of just, that's sort of the bigger picture. And by the way, if there are questions or comments throughout, just feel free. So a couple of years ago, I was on sabbatical at Princeton, and I gave a talk about some of the work we had done on invariant inference. And Dave Walker, my host, said, "Oh, how about, could you do this for representation invariance for data structures?" And he was teaching representation invariance in his undergraduate class, and so we started this project, and that's what I'm going to tell you about today. So Anders Miltner was one of Dave's PhD students. He's now a postdoc at UT Austin. And Sashwat Padi was my PhD student who also did the prior work that I was involved in on automated invariant inference. That was his dissertation work, and he's now in Amazon at the Automated Reasoning Group. Okay. So a representation invariant, I'll tell you what it is more specifically, but basically this is about trying to prove that a data structure implementation meets the specification of the data structure. So here's a simple kind of interface for integer sets of integers. So this is using sort of OCaml style or functional style. So the interface for a set is it's some abstract type T that has an empty value representing the empty set, and it has different operations like insert, delete, lookup. And then there's a specification, and this isn't a full specification, but you could do a full specification. But just for example, you might want to prove that looking up anything in the empty set gives you false, and looking up something after you've inserted it is always true, and looking up something after you've deleted it is always false. So now here's an implementation again in OCaml of this set, and here what I'm doing internally is I'm using an integer list as my representation of the integer set. And then I implement all the operations in terms of integer lists. And so that's fine. And now we can go ahead, and you could do this in Coq too. Coq has a language that's very much like OCaml. So I could write all of this up in Coq, and then I could try to prove these things. And if I do that, I'll find that, yes, I can prove that, for example, looking up something in empty always returns false because empty is the empty list, and looking up in empty returns false. So that's fine. And if you think about it for a second, you can prove that the insert property holds as well. But if you try to prove the delete property, that deleting something returns, and then looking it up returns false, if you just directly try to prove it, you won't be able to prove it in Coq or in any interactive proof assistant. You'll get stuck. One poor thing about those tools is that you won't get a counterexample. You'll just get stuck trying to prove the thing. But I'll tell you a counterexample. Here's a counterexample. If I give an input list 0, that's this list 0, 0, and I delete 0, then if you look at what this thing does, it only deletes the first occurrence of something. So it'll actually leave you with the list 0 remaining, and so that means that looking up 0 and that thing will still return true. So that's why I won't be able to prove this. But of course, in fact, this code is correct. That's not a valid counterexample, even though I won't be able to prove it. And so why is it not a valid counterexample? Well, for kind of a standard reason, but in the context of data structure implementation, it's like this. There's a set of all integer lists, but there's the subset of all integer lists that are actually reachable, actually constructible through the module interface. And in fact, that one is not constructible through the module interface because the module is carefully ensuring this invariant that the lists it's creating have no duplicates. And that's kind of implicit, but insert, for example, is doing that because it's not adding something unless if it's already in the list and so on. And so, yeah, so 0, 0 is kind of outside of the set of actual reachable integer lists that represent sets. And so this leads to kind of the standard style for proving that a data structure implementation meets its interface, which is to identify an invariant, call it the representation invariant. It's some predicate on the set of integer lists, and it has to have two properties. One is that it has to imply the specification, so it has to be stronger than the specification. And the other is that it has to be weaker than the set of all reachable integer lists, or it has to include the set of all reachable integer lists, or another way to say that, it has to be inductive, meaning it has to be preserved by all the module operations. And so if you can identify such an invariant, and you can prove that it implies the spec and it's inductive, then you're done. Then you've proven that your module meets the spec. And so, yeah. And so in our case, in this particular example, here's an inductive invariant that works. It's written as a recursive function. Let's just say a predicate that says there's no duplicates. And so if I claim that that's my representation invariant, then I have to prove two things. One is I have to prove that integer sets or integer lists that satisfy the invariant imply the spec, and that's going to be true. That happens to be true. Like that 0, 0 list is no longer applicable because it doesn't satisfy the invariant, so we don't have to consider it. And we have to prove that it's inductive, and you do that just kind of module operation by module operation. So I can prove that empty has no duplicates because empty is just the empty list. For insert, you have to prove in the normal inductive way that if insert is given it a list that satisfies the invariant, then it will produce a list that satisfies the invariant. And I can go through and prove all these. And so that's how you would manually prove that this integer list satisfies its set specification, that the module satisfies its set specification. And this is how things are done. So like there's a book, Andrew Appel has this book on verified functional algorithms. It's full of data structures implemented in Coq that are proven correct using this way. But again, the human has to figure out, the programmer, the tools, the automation doesn't help you at all with this. You have to come up with the inductive invariant, the representation invariant. The automation will help you prove these two things, but you have to come up with the invariant yourself. And the invariant has to be strong enough, but not too strong and not too weak. And if you get that wrong, then you're on your own to kind of go and fix that and whatever. So this is sort of an opportunity for automation, and in particular forms of program synthesis, to say, can we help people to synthesize valid, sufficient representation invariants to prove that their data structures are correct?
So the quick question before you go on to I assume the core of the talk. Can you comment on the connection between sort of the hierarchy that we see, right? And proving full versus partial correctness of a data structure, right? So sometimes we just want to prove something that does not guarantee full correctness, right? We omit some property. Is there a connection between, say, the reachable and the invariant and the list satisfying specification not being the same set, but being sort of strict subsets of each other, and proving full correctness? Or these two things are completely orthogonal from each other?
So let me give an answer and see if that's what you're asking. The way I think about it is, so the invariant, the invariant that you need, there can be many invariants that work, and the invariant you need just has to satisfy these properties. So if the spec is weaker, then the invariant can be weaker. So for example, so definitely there's nothing that requires this to be a full spec. Like, so as a simple example, let's say that all I cared about is this very first property, and I didn't care about the other properties. Then in fact, my representation invariant could just be true, because I don't need to know anything more about the list module other than what's already, I don't need to know anything more about the list module than what's already here. There's no other invariants that I need to depend on in order to prove that. So even though the module does maintain a much stronger invariant than true, true would be a sufficient invariant just to prove that spec. And so depending on, and so this happened in our experiments too, depending on what spec you're trying to prove, you might, with a weaker spec, you might need essentially like a true representation variant or a very weak representation variant, but the stronger properties you want to prove may need more stronger representation invariants in order to justify them, in order to prove them.
So that makes sense. Now, in your specific case, it seems that you are proving full correctness, right, of the three properties, right?
Technically not, because you'd also have to show that, I mean, there are a couple of things missing here, but you have the positive case of insert, that if you insert something and then look it up, then that's fine. You'd also need a case that says if you insert something and then you look up some j that's not I, then it's equivalent to looking up in the old set, looking up j in the old set. So there's a couple of things missing here, but maybe that's, but I don't know if that relates to your question or not.
I think that was essentially my question. I could ask more, but let's go on. It was very useful. Thank you.
Yeah. So the bottom line is that kind of like to say with a loop invariant too, like the loop invariant that you need to prove some property depends on the post condition that you're trying to prove, the property you're trying to prove. So the invariant is some internal thing just for the proof, and so it's how strong it needs to be depends on how strong the spec is, and so yeah, that's the main point. Okay. Right. So what we've done is we've built this algorithm and an associated tool called Hanoi that takes these three things, your interface and your implementation and your spec, and it spits out a representation of it. And of course, it's not quite magic like that because it's solving a really hard problem. And so we'll see that there are some so there's some limitations on it, but this is kind of the goal we set ourselves: is can we generate these sufficient representation invariants just given these three things. Okay, and so what we did was we created this data-driven algorithm for doing that. We formalized it and proved some properties about it that I'll tell you about. We implemented it and we've evaluated it on a bunch of Coq data structures. So the algorithm is a data-driven algorithm, just like other data-driven algorithms for synthesis. And so it actually combines synthesis and verification. It uses then two black box tools, a synthesizer and a verifier. This is a very standard setup. So the way we're going to do things is we assume we've got a synthesizer, and it can be, we're not innovating there. We're just given a synthesizer, and what it does is, given input-output examples, it generates a program that meets those examples. And in this case, our programs are going to be predicates. They're going to be invariants. And then that's a candidate invariant. Then the verifier will check it and say either yes, and we're done, or no, and here's a counterexample. And so that becomes a new example for the synthesizer. And so here's how this works. Let's say we have a bunch of positive and negative examples, and we'll start out with no examples in the beginning, but at some point we have some, so in our case, they're positive and negative examples whose output is true and examples whose output is false. Those are the examples for the synthesizer. We generate some invariant. The first thing we can do is check, does this invariant imply the specification? That was one of the things we have to check. So like in our case, we can check, in our example, we could check whether now the invariant implies the spec. If that's true, if that's valid, we'll move on. But if that's not valid, the thing you have to do is figure out, okay, well, this counterexample you'll get back, is that a new positive example or is that a new negative example? And in this case, it's pretty easy to see that it's a new negative example. Why? Because something that violates this condition is a list, an integer list in our case, that satisfies the invariant but violates the spec. And so if it satisfies the invariant but violates the spec, if the spec is actually true, then that means that the invariant is too weak. It's including this integer set that it shouldn't be including. So we should treat that set as a new negative example. And that will force us to generate a stronger invariant the next time around that doesn't include that example. So that's fine. And then you want to check, then you need to check, is that invariant inductive? And this is where the more interesting thing happens. If that's valid, then you're done. But if it's not valid, the real hard part about kind of doing data-driven invariant inference for inductive invariants is that it's not clear when you get a counterexample to inductiveness whether you should treat that as a positive or a negative example. And let me show you why that is. So here's a really bad candidate invariant, which is that the length of the list is less than 2. But I'm just using that as an example. Let's say at some point in our algorithm, you say the candidate invariant is that the length of the list is less than 2. That holds for the empty list. When we try to prove that that's inductive for the insert operation, what we'll find is that it's not. And here's a counterexample. I can give a list whose length is less than 2, like the list containing 1, but after I insert, I get something whose length is equal to 2, and so that violates the invariant. The fundamental issue is that there are two ways to resolve this counterexample. So what a counterexample to inductiveness is, it's a pair. It's a pair of a pre-state that satisfies the invariant and a post-state that violates the invariant. And so one way to go is to say, well, I need to strengthen the invariant to eliminate that guy. Or the other way to go is to say, no, I need to weaken the invariant to include that guy. And either one of those would be a way to resolve that counterexample, but I don't a priori kind of know which is the right way to go. And so that leads to kind of a combinatorial explosion if I have to kind of search for, search in both directions for every inductiveness counterexample. So the observation we make, which is quite simple, is that consider the special case when we happen to know that this list one is actually reachable. It's actually a constructible representation of a set. In that case, then there's no choice, because if it's reachable, then that means it must be included in the invariant. And if it's reachable, then that means that this guy is also reachable because we can obtain it by calling insert on this guy. And therefore, the only thing to do, therefore, this is also a reachable set representation. And therefore, the only thing to do is to include it in the invariant. And so that leads us to define this notion of what we call visible inductiveness, which will say that an invariant is, a candidate invariant is visibly inductive if it's inductive relative to the known set of reachable values. So it's not necessarily fully inductive, but it's inductive relative to the known set of reachable values. And so what we're going to do, and I'll show you this in a moment, is that we're going to carefully maintain in our algorithm that all the positive examples we're maintaining are known to be reachable. They're known to be constructible through module operations. And so what this lets us do is we can check visible inductiveness by checking inductiveness relative to the current set of positive examples. And so when I go to check visible inductiveness on insert, I'll check it just with respect to these examples, saying if S is one of those examples, then does the output satisfy the invariant? In this case, we still get that same counterexample because the list one is in our set. But now we know that the only thing to do is to weaken, because we know the list one is reachable. It's in our positive examples. The only thing to do is to weaken and include 0, 1. So I haven't really, so let me show you how we use that and why that's useful. So what we're going to do now is, back to our algorithm, after we get to the point of ensuring that the invariant is strong enough to imply the spec, we want to check inductiveness. But we're not going to check inductiveness right away. We're going to check visible inductiveness. And so what this is going to have the effect of doing is kind of forcing us to eagerly weaken. It's essentially saying, let me deal with all the forms of inductiveness that I know I don't have to be non-deterministic about, that I know how to deal with. Let me try to deal with those eagerly. So I'm going to iteratively weaken until I'm visibly inductive, because I know that in those cases I have to weaken. And one way to think about that conceptually is what we're doing is we're saying we have some frontier of known reachable things. And visible inductiveness is making sure that that frontier, if you take any one step further from that frontier, like you insert or you delete, you're still satisfying the invariant. So it's sort of checking one step inductiveness. So we're gonna weaken until we're at least sort of one step inductive. And then we'll check full inductiveness. Now, at that point, we still have the problem that you don't know when you get a counterexample whether to weaken or strengthen. But given our algorithm, there's actually only one thing we can do, because at this point, because the invariant is visibly inductive, any full inductiveness counterexample will have the effect that will have the property that the pre-state is not known to be reachable. If it were known to be reachable, then this would be a counterexample to visible inductiveness. So we can't weaken here, because that would violate our invariant that all the positive things are known to be reachable. So the only thing to do here is to actually strengthen at this point, treat the pre-state as bad. That may turn out to be wrong, because we don't know whether the pre-state is reachable or not, but we'll correct that kind of the next time around when we go and try to again check visible inductiveness. So what's happening is that the positive examples are sort of maintaining true positives, really reachable things. And the negative examples are just maintaining things that are negative relative to the current inductive invariant candidate, They may or may not be really negative. And we'll find that out as we go around again. And so in fact, because of that, every time we weaken, we have to actually, you could maybe be smarter about this, but we just completely empty out the negative examples, because again, the negative examples aren't necessarily true negatives. They're just negative relative to a current candidate invariant. And so this is the idea. So basically, strengthen to the spec, you weaken to be sort of one-step inductive, and then you treat the other inductiveness failures as negative, but they are correctable in the next time around.
Oh, the quick question.
Yeah.
I assume you considered just asking a reachability query on a counterexample, right? And rejected that idea. Why is it? Is it because it's so hard to solve in general?
That's a good question. I don't know. I mean, so I guess that's something you could consider. I guess if the module is simple enough, you mean just sort of explore up to some boundary, or like just try to run the module or simulate the module up to some bound of interactions. I guess you could do that. I mean, in some sense, what the algorithm is doing is iteratively doing that frontier exploration anyway. So in some sense, that's what's happening. But yeah, actually, I mean, maybe that could be a way to go. You can just eagerly try to search for a reachable, search for it being reachable.
So can you recap for us how deep is that backtracking? So if you follow that outermost loop, right, where you check full inductiveness, you assume it's a negative example. Now, at that point, you flush the negative example from upper left, right?
So at this point, we add a negative example, and we don't change anything. We just add a negative example. But what's going to happen is, let's say I put something in the negatives that's actually should be reachable. Then eventually, when I check visible inductiveness, I'll actually catch that. I'll see that basically. In some sense, what's happening is the visible inductiveness check is in expanding our reachable frontier. And so you could do what you suggested, which is eagerly be reachable, but the visible inductiveness check is essentially eagerly is sort of doing the one-step expansion of the frontier of known reachable things. And so what happens there, it's not really shown here, but if we expand the frontier and that includes something that's currently in our negative set, then we know that that's really a positive and should be moved to the positives. And by emptying out the negatives when we do that, we kind of avoid having a conflict, like a false conflict where something is considered both positive and negative.
I see. But that might take several single-step expansions, right?
True.
Okay, right.
Maybe the reason that it worked okay is because counterexamples tend to be small. It depends on how you get counterexamples. But if you get, if you're going to get a counterexample that's size 20 list, then you'd be in trouble. But if you're going to get small counterexamples, then maybe this works okay. So yeah.
Get it. There is a question in chat from Karam. Are the synthesized invariants always universally quantified? Or are there scenarios in which universally quantified invariants are insufficient?
That's a good question. So the theory works more generally, but our tool only supports sort of our implementation only supports being universally quantified at the front. So yeah, definitely if you, for many, there are natural examples where you say for all this, there exists a Y such that whatever. So those things, fit in the theory of representation invariance. And I think nothing in this algorithm depends on being universally quantified just at this level of abstraction. But our implementation only supports, sort of universally quantified at the front. Yeah.
Thank you, Todd.
Great, thanks. So that's kind of the algorithm at a high level. What we've done is we have this kind of type-theoretic formalization where we formalize this in the traditional style for modules, where a module type or a module interface is an existential type, where it's existential over the unknown implementation type of the module. So that's like the T in our example. That's the set type alpha. And then that's the type of the module itself, the set of operations that the module supports. And the implementation is a pair of a concrete implementation type for alpha, that would be integer list in our example, and then the actual module value. And we'll see the benefit of this in a minute. But so we can formalize our problem then as given such an interface and given such a module and given a specification, which yes, is actually in our formalization universally quantified at the front, then we're trying to find a representation invariant, a sufficient representation invariant, which we denote this way. And the key thing in our formalism is that we need this notion of well, we need full inductiveness, and we also need this notion of visible inductiveness. So what we've done is develop this type index logical relation, which kind of generalizes both of them, which we call conditional inductiveness, which you can read as saying that a value at a particular type is conditionally inductive for Q relative to P. So think of P as the pre-state and Q as the post-state. And so when they're the same invariant, like let's say they're both I, then that's checking full inductiveness. But this could be something like the set of reachable known things, and then this is I, then that's our visible inductiveness. So this is a more general form of that for conditional inductiveness, conditional relative to a pre-state P for a Q state, a post-state Q. You don't have to read all of these things, but the key advantage of using the type theoretic approach is that we can now easily lift things to an arbitrary module type. So here we're showing how to deal with pairs, which can lift to arbitrary tuples. Here we're showing how to deal with functions. And for example, you have the contravariance on the argument and the covariance on the result. So what this means is that, for example, one thing I didn't show is like, for example, sets. Let's say all the examples in the set that I showed you have a single element of the abstract type as an argument, like insert, delete. But there are things like union on sets or intersection on sets, which take two sets and return a set. And so this tells you sort of how to lift the algorithm directly to situations like that, where you actually have, where you have functions, for example, that take two sets as an argument and return a set. And here we're showing how do you get counterexamples when it's not valid. And again, how do you get counterexamples from pairs? How do you get counterexamples from functions and things like that? So in fact, the formalism is limited to first order functions, but the implementation actually also handles higher order functions. So we can get counterexamples from higher order. This actually is a sound notion of what it means for a higher order code to be conditionally inductive. But then this only models how to get counterexamples from first order code. But in the implementation, we actually handle higher order code as well. So you can do some form of higher order contract checking to actually get counterexamples even to higher order functions. So you could, for example, have a set data type that has a map operation, which is a higher order function on it, and you can and this will show you how to check inductiveness of that and how to get inductiveness counterexamples.
Todd, we probably have 5 minutes to the end. We are now at 30, but of course there are questions. So I don't know what you want to cover in the 5 minutes, and then we'll have more questions, I'm sure. Okay, sure. So yeah, I can go pretty quickly. So a couple of properties we have. One is soundness. So here we're assuming that the underlying verifier, that the algorithm is parameterized by a verifier and a synthesizer. I assume the verifier and synthesizer are sound and complete for normal definitions of what that means. Under those strong assumptions, then we can prove that Hanoi is sound. If it generates an invariant, then in fact, that's a valid representation invariant. And it's also complete for a special case. It's complete in the case when the implementation type is finite. That is a pretty strong restriction. It's a restriction on the theory that implementation supports data types that have infinite number of values. But I would argue that even this is an interesting result, even when the type is finite, because if you remember what the algorithm is doing, it's kind of ping-ponging back and forth between strengthening and weakening the invariant. And so it's not obvious that it won't get stuck in some kind of loop of strengthening and weakening. And so what this shows is that, at least for this special case, it will eventually find an answer. And in fact, I don't know of any the prior inductive invariant algorithms, data-driven ones that have a completeness result are really kind of trivially complete because they just do some kind of bottom-up enumeration or something. So this is doing something a little bit smarter. It's kind of ping-ponging back and forth between weakening and strengthening, but we can still show this kind of special case of completeness. So we implemented this with Myth, which is an existing synthesizer that synthesizes recursive functions in functional programs. And we used an unsound verifier. So we just did enumerative testing for verification. Of course, that's unsound. But the benefit is that it's fast and it terminates, and it sort of supports our use case where we're not necessarily trying to replace the prover. We're trying to just help the prover give suggestions. So we took a bunch of benchmarks. Here's really the bottom line is that we ran it with a timeout of 30 minutes. We were able to actually infer 22 invariants out of the 28 cases we tried. And all of the invariants were actually sufficient representation invariants, even though we were just using kind of an enumerative tester instead of a sound verifier. The key limitation was that
the underlying synthesizer can only generate a single recursive function. It can't generate functions that need helper functions and also generate those helper functions. And so whenever we needed an invariant that couldn't be written as a single recursive function, or at least couldn't easily, that's sort of why we got these 6 failures. You don't really have to read this, but the key point that's interesting is that when it succeeds within a couple of minutes. Otherwise it times out. And we're handling, a bunch of real data structures from the Coq library, sets and binary trees, binary search trees, queues, priority queues, things like that. I'll quickly talk about related work if I have a minute or two. I think the closest related work is other work on data-driven invariant inference. There's been prior work on data-driven loop invariant inference, including my own prior work. That's really a special case of this setting. You can think of a loop as a module that has a single operation of type T arrow T from pre-state to post-state. That's it. And so this is really kind of a more general setting. CHC solvers or constrained horn clause solvers are in some ways more general than the setting we're considering because you can have multiple unknown invariants that you're solving for. And there have been some data-driven approaches there, but they've typically only supported arithmetic constraints. They haven't considered the kind of constraints that we have on data structures, recursive data structures. And also higher order functions, which we handle in our implementation, don't fit into the sort of CHC framework. We've defined this notion of visible inductiveness. Interestingly, there's kind of a dual notion in the literature of conditional inductiveness that's been used in static techniques for invariant inference, where it kind of goes backwards. So the idea is that if you know that the post state in an inductiveness counterexample leads to a bad state, then you know the pre-state also leads to a bad state and therefore is also bad. And so that's kind of like a backwards approach of what we're doing. The forward approach that we're doing is more natural in the data-driven setting where we kind of have actual concrete examples that we're running, concrete tests that we're running. And there's only one other work that I know that's specifically on trying to infer representation invariants. They do this for Java code. But they kind of just have a fixed language of predicates, and the invariant must be sort of a Boolean combination of those predicates, and they don't have any sort of guarantees as a result on the resulting invariants. Sanjit, did you have a question?
I do, but I can wait for you to conclude, and then I'll ask.
Oh, okay. So yeah, that's basically what I wanted to say. I think I've shown you this data-driven inference technique for representation invariants, and we introduced this notion of visible inductiveness. The type-theoretic formalization is useful in sort of lifting to arbitrary modules, at least arbitrary in the formalization, arbitrary first-order modules, in the implementation, including higher-order modules. And I told you a little bit about the implementation evaluation. And kind of popping back up, what I want to say is that really program synthesis can be a key enabling technology for program verification. That's kind of the idea here. So we're synthesizing invariants kind of links synthesis to verification in an interesting way. So that's it. Thank you.
Thank you, Todd. Let's open the floor for questions. Sanjit, I assume you want to.
Yeah, let me go ahead. So thanks, Todd, for an excellent talk. My question was about your other work on Cygus solving, loop-in-gen. And I wanted to understand how the approach used in loop-in-gen relates, if at all, to the approach that you presented today. You know, what aspects are similar and what's different with loop-in-gen, which is your approach to Cygus solving?
Okay, yeah, thanks. So I don't know if I had a little trouble hearing. I don't know if other people did too, but I'll repeat the question. So I think the question was about, so we have prior work on loop invariant inference. We had a tool called loop-in-gen, and we've done a bunch of work on that over the years. And the question was how this algorithm relates to that algorithm. So there are a couple differences. One is that, again, loop invariant inference is a special case where you can think of it as a module that has a single function. For a single loop, it's just a single function of type T arrow T. It takes a pre-state to a post-state. And so we had to figure out how to generalize to things where you have multiple, like a function of type T times T arrow T. So you take two instances of the type to the type. So generalizing to multiple counterexamples for an arbitrary first order type instead of just a loop was one thing. The other key difference in the actual algorithm is that LoopNGen actually uses this heuristic where it doesn't do this invisible inductiveness thing. It actually does heuristic strengthening. So what it does is more like, it actually does something that's kind of more like what these people do. So if we get an inductiveness failure on some invariant I, it will try to find an I prime that it can conjoin to I to strengthen the invariant, and then try to find an I double prime that it can conjoin. So it kind of uses this heuristic of heuristic strengthening, and then if it over strengthens, it'll only find that out sort of at the very end. And so what we realized was that actually LoopNGen sometimes fails because of that, because it goes down a wrong path and it heuristically strengthens, and it's already on the wrong path, but it's going to keep strengthening and strengthening and strengthening until only much later it finds out that it's wrong. And so the visible inductiveness thing, what it does is it actually forces you to kind of weaken early. And so in LoopNGen, we were only weakening at the very end when we found some kind of contradiction between the pre-state and some overly strengthened invariant. So I think this eager weakening is actually really useful because it kind of keeps you honest. You strengthen and then you eagerly weaken. And I think that's more generally useful beyond this tool. Like it would be actually useful to port that back to LoopNGen, for example. Yeah.
Thank you, Todd.
Thanks.
Do we have additional questions? Well, if not, let's thank Todd again.
Thank you.
And we have Elizabeth here. Elizabeth, could you